Hey everybody, and welcome to our second lecture in discrete math. I'm going to recap something that we did in class yesterday and give a couple of examples, and then we'll move on to new stuff. Another example of a compound statement or compound proposition. And from now on, I'm going to use the words proposition and statement interchangeably. Another example of a compound statement or a compound proposition is the conditional statement, which I guess implies that it's true under certain conditions. Here is how the conditional statement is written symbolically. It connects the statements P and Q with this arrow pointing to the right. And here's how we interpret this statement in English. We interpret this as if P, then Q. If P, then Q. Now I can expand this a little bit. Here's the sense of it. What this is really saying is that if P is true, then Q is true. So if P, then Q. That means if P is true, then Q is true. So anytime we have an if-then statement, that's a conditional statement. An if-then statement is a conditional statement. If P is true, then Q is true. Now here's an alternate interpretation of the same statement. Sometimes we look at this and we say, P implies Q. P implies Q. So we can look at this arrow as meaning implies. P implies Q. Now in English, what this really means is that P is true implies that Q is true. So P being true implies that Q is true. That's our alternate interpretation. And these two interpretations are equivalent. Now, to get the sense of exactly what this means and exactly what it doesn't mean, let's look at an example. Here's an example of an if-then statement. If you give me $10, then I will wash the car. This is me talking to my father, and apparently I'm not a very appreciative son. I'm not going to wash the car for nothing. I'm going to make sure he pays me $10 before I do it. In this case, the statement P, or the proposition P, is you give me $10. And the statement or proposition I will wash the car is Q. And we put the arrow right here. If you give me $10, then I wash the car. Or you give me $10 is true implies that I will wash the car. Now let's analyze this from our own experience and from our own interpretation of the English language and see exactly what this means and exactly what this doesn't mean. First of all, in an if-then statement, the assumption is that P is true. And so in an if-then statement, if P is true, it's assumed that true is going to be, it's assumed that Q is going to be true also. No guarantees are made here in the situation where P is not true. The conditional statement just explains what will be the case if P is true. So let's examine this. Let's say that my father gives me $10. Then P is true. And let's say that I wash the car. Then Q is true. Am I happy? Yeah, I got my $10. Is my father happy? Yeah. He gave me $10, I washed the car. I did what I was supposed to do. In my father's mind, have I lied to him? No. I said that if he gave me $10, then I'd wash the car, and that's exactly what happened. So in my father's mind, I told the truth, which I did. So when P is true and Q is true, this compound statement or compound proposition is true. Now let's look at another case. My father gives me $10, and I'm such a rotten son. I don't wash the car. Is my father happy with me? No. Have I lied to my father? Absolutely. I told him that if he gave me $10, I would wash the car, and I didn't do that. I lied to my father. So if P is true and Q is false, then the statement is false. In other words, if we have a true statement implying a false statement, the compound statement or proposition is false. True implies false equals false. Now let's look at some other cases. Let's suppose that my father doesn't give me $10. So P is false. And since my father doesn't give me $10 and I'm such an ungrateful son, I don't wash the car. Is my father mad at me? No, maybe a little disappointed, but he's not mad. Have I lied to my father? No. I didn't say that I would wash the car if he didn't give me $10. So if P is false and Q is false, I haven't lied. This statement is still true. Now let's look at the last possibility. My father doesn't give me $10, but I'm remorseful and I say, you know what? My mother and father feed me, they clothe me, they give me a place to live. If there's something that I really need, they make sure I have it. I don't need to get $10 to wash his car. I'll wash it for nothing. So my father doesn't give me $10, but I wash the car anyway. So P is false and Q is true. Is my father mad at me? Nope. In my father's mind, have I lied to him? No. Because I didn't say what would or would not happen if he didn't give me the $10. So if P is false and Q is true, I've told the truth. Those are the four cases, the four possible cases. And what we want to do is we want to know the special case, the one that we need to remember. When was it? When was the only case here when this whole statement was false? Wasn't it when my father gave me $10 and I didn't wash the car? That is, when P is true and Q is false. That's the only time when a conditional statement is false. So let's make a record of that, the special case of a conditional statement. Okay, here's our special case for the conditional statement. The conditional statement P implies Q, or if P then Q, is only false when P is true and Q is false. In other words, anytime we have a conditional statement where we have true implies false, the statement is false. True implies false is false. All other cases are such that the statement is true. So, let's do the truth table for a conditional statement. Here's our assignment. Construct the truth table for the conditional statement P implies Q, or if P, then true. So we have two statements, P and Q. And we might remember that when we have two simple statements, P and Q, there are four possible combinations of truth values for the two statements. And the way that we list them all is we go true, true, false, false on the outside. And on the inside, we alternate true, false, true, false. And this is the universally accepted way to set up a truth table made up of two simple statements, P and Q. And here's the statement, P implies Q, that we want to construct a truth table for. Do I have this truth table memorized? Well, I'll confess, I don't. I don't know what it looks like, but I have something that's just as good as having the truth table memorized. I know the special case for a conditional statement. I know that the only time that this conditional statement is false is when I have P true implying Q false. That is, when I have P true implying Q false. That's the only time that this statement is false. I know the special case for this statement, and that's just as good as having the truth table memorized. So where in this truth table is P true and Q false? Right here, isn't it? And in this situation, the statement P implies Q is false. Now, what about the other statements? Well, I don't have to think about it. This is the only time when the statement is false. All other times, the statement is true. So flying on autopilot, as I love to do without thinking, I know that I can just fill in the rest of these with the true symbol, T. And then I will circle this column. There. That's the truth table for a conditional statement. Here's a good example for us to work on. Construct the truth table for the statement P implies Q and Q implies P. Well, it may not seem like a good example, but there's a reason why I want to do this example. You're probably wondering, why on earth would we want to know the truth values of that statement? There's a reason. So let's construct the truth table. First of all, let's look up here and see how many simple statements we have. This entire statement is constructed solely from the simple statements P and Q. So our truth table will be set up for two simple statements, P and Q. So here's our P, here's our Q. And we remember there are 4 possible combinations of truth values for this pair of statements. And the way we set this up, we go true, true, false, false on the outside. And we alternate true, false on the inside. What comes next? You know, in the broadest sense, this whole statement is a conjunction. It's this thing and that thing. So I guess in order to figure out the truth values for this whole statement, I have to figure out the truth values for this thing first, and the truth values for this thing first, and then I can figure out the truth values for this thing and that thing. So I need the truth values for P implies Q first. P implies Q, or if P then Q. This is a conditional statement. What's the special case for a conditional statement? The special case is true implies false equals false. So do we have P true implying Q false? We sure do. Here's P true implying Q false. This is going to be false. And we know that all of the other cases are true. So without even thinking, I just put a T in those other cells. I just love it when I don't have to think. So that takes care of the statement P implies Q. Now we also have to come up with the truth values for Q implies P. This again is a conditional statement. And the special case is going to be when we have false implies true. In other words, when we have Q false, and no, I beg your pardon, I'm way off base. The special case is true implies false is false. So we're looking for the case when we have Q true and P false. If we have true implies false, this statement is false. So when is Q true and P false? Isn't it right here? In this situation, we have Q true implies P false. So in this case, the statement is false. Q is true, P is false. We have true implies false. That's false. Now, what about the other statements? Hey, they're automatically true. I'll put down true in each of these cells without even thinking about it. So I've taken care of this statement. We've taken care of that statement as far as truth values go. Now I think we can do the whole thing. We can find the truth values for this thing and that thing. This is an and statement, a conjunction. What's the special case for an and statement or a conjunction? Isn't the special case when both of these are true? The only time that a conjunction or an and statement is true is when both of the statements that make it up are true. So where does that happen? When is this thing true and this thing true? Well, this thing is true here, and this thing is true here. This is the only case where it happens. In all of the other cases, one of these things or the other is false. So this is the only situation right here where this statement and this statement are both true. So I put a big fat true here. Let me make that a little bit fatter. And all of the others I know have to be false. I don't even have to think about the truth values because I know my special case for an and statement or a conjunction. I know that all of these other things are going to be false. Whoops. Wait a minute. This thing is true here, and this thing is true here. Son of a gun, it happens twice. Well, I'm just going to have to make a correction here. Son of a gun. There are two situations when this statement and this statement are true simultaneously. It happens right here, and we have a true statement. It happens right here. So our conjunction is going to be true here also. Oh, you know what? That looks so much better. Actually, I do have this table memorized, which is why I was in shock when I saw true, false, false, false. And I said, no, that's not the right table. Okay, we've got everything right now. This is the truth table for P implies Q and Q implies P. Are we going to memorize this table? No. We're just going to remember the truth values. We're going to remember the truth values for about another 5 or 10 minutes, and then we won't really care about this statement ever again, I don't think. But we want to remember how the truth values turned out here. And let's see, when was this thing true? This thing was true when both P and Q were true. And this thing was true when both P and Q were false. The other two times, when one was true and one was false, the statement was false. Okay, we'll remember that for another 5 or 10 minutes. There's a reason why we want to remember this for another 5 or 10 minutes. And then we'll forget it, sort of. Okay, this is the last of our compound statements that we need to know the truth values for. It's called a biconditional statement, and the prefix bi means two, like in bicycle. So essentially it's saying we have two conditional statements here. And we have an arrow that points both ways. So essentially what this is saying is P implies Q, and since the arrow goes this way too, Q implies P. Now how do we interpret this? We see this and we say P if and only if Q. And in English what that really means is that P is true if and only if Q is true. Another way of looking at it, P is true exactly when Q is true. And finally, another way of looking at it, P implies Q and Q implies P. Considering the symbol up here, that makes sense because we have the arrow pointing from P to Q, so P implies Q. but we also have an arrow pointing from Q to P, so Q also implies P. This is not the most common rendering of this symbolic statement, but it probably makes the most sense. P implies Q and Q implies P. In other words, P being true implies that Q is true, and Q being true implies that P is true. And this last interpretation will help us get the truth table for this biconditional statement very easily. Our last interpretation of the biconditional statement was P implies Q and Q implies P. That's this thing right here. P implies Q and Q implies P. So the biconditional statement, P if and only if Q, or P is true exactly when Q is true, this biconditional statement is logically equivalent to the statement P implies Q and Q implies P. Now, when I say logically equivalent, what do I mean? I didn't do that very well. That looks a little bit better. So if the two statements are logically equivalent, that means they have the same set of truth values. Or another way of saying this is that their truth tables are the same. That's why in our last example we were interested in getting the truth table for this statement, because the truth values of this statement are exactly the same as the truth values for this biconditional statement. So let's write the truth table for this statement and see if there's a special case. Okay, let's go for it. We still have two simple statements. So we fill out the truth table this way: true, true, false, false. And on the inside, we go alternately, true, false, true, false. And we're constructing a truth table for the biconditional statement P if and only if Q. Now, we might remember from this example that this thing was true when both P and Q were true. And this thing was true when both P and Q were false. The other two times this statement was false. So this is the truth table. For the biconditional. I guess we could describe a special case two different ways. I'm going to opt for the special case when the biconditional is true. When the biconditional is true, either both P and Q are true, or both P and Q are false. So what I'm going to say is that the biconditional is true exactly when both statements have the same truth value. They're either both true or they're both false. So when they're both true or they're both false, the biconditional statement is true. It's false all other times. Since most of us taking this course are in computer science, we should take applications to computer science wherever they arise. And this is one of Boolean logic. A Boolean variable is a variable that has exactly one of the values true or false. So a Boolean variable is either true or it's false. It has to be one or the other, and it can't be both. Now, a bit is actually a variable that can assume exactly one of two values, 0 and 1. Everything in computers is broken down to bytes, and then it's broken down further into bits. And a bit that has a value of 0, we would say that that would be essentially the same as being false. A bit that has a value of 1, that would be the same as the bit having a value of true. So logically, we take a bit that can have exactly one of two values, 0 or 1, and it must have one or the other. And we say, you know what? This is very similar to a Boolean value that can have only the values of false and true, and it has to have one or the other. So when a bit has a value of 1, essentially we look at that bit as being true. When a bit has a value of 0, we look at that bit as having the value of false. And let's build on this. Since bits are essentially the same as logical variables, it makes sense that we can perform logical operations on them, like with the disjunction operator or the conjunction operator and, or the exclusive or operator, and the negation operator. So let's do truth tables for x and y for each of these logical operations. Well, let's see. X and y, we don't write them as true and false, do we? If x and y are bits, we don't write them as true or false. We write them as 1 or 0. And we interpret 1 to be true and 0 to be false. So I guess we'll fill out the truth table this way. True, true, false, false. True, false, true, false. There, how's that? And for a disjunction or an or, what's the special case? They're only false when both are false. Okay. Well, here they're both false. So the statement X or Y is false. All other cases, they're true. You know what? That wasn't hard at all. Well, we made short work of that one. Let's do the conjunction next. Here's our table for the conjunction, X and Y. And I might just write that above, X and Y. Because when we're working with bits, a lot of times we use the words and, or, XOR. Let's fill this thing out. On the outside, we have true, true, false, false. And on the inside, we have true, false, true, false. This is an and statement or a conjunction. What's the special case for a conjunction? If you said a conjunction is only true when both statements are true, you're right. So here's our special case. And here X and Y are both true. So this is true. The rest of the time, they're all false. So this is our truth table for the conjunction of bits X and Y. Now we're going to do the exclusive OR. Okay, we got our table set up for the exclusive OR. And we could say this is X XOR Y. And we fill out the truth table. On the outside, true, true, false, false. On the inside, true, false, true, false. And the special case for an exclusive OR, son of a gun, there are two, I don't remember which one I gave you. It's only false when both have the same truth value. I'm not sure if this is the one I gave you or not. It's only true when truth values are different. So let's see, here the truth values are different, here the truth values are different. So we have true, true. Now this says they're only false when both have the same truth value, the same truth value. Here they're the same, this is false. Here they're the same, this is false. So we can use either one of those special cases. I apologize, I don't really remember which one I told you in class, but you can take either of these, whichever seems easier to remember to you. Take it and run with it. And here's our truth table for exclusive OR. And we have one more truth table to do, and this is pretty trivial. It's the negation truth table. So we only have one variable, x, and the variable x can have exactly one of two truth values. It can either be true or it can be false. And here's the statement not x, or the negation of x. And what does the negation operator do? It changes true to false, and it changes false to true. So this is the truth table for not x. The next thing that we do is we need to define a string of bits, or a bit string. Our author says a bit string is a sequence of 0 or more bits. I don't know why we'd have a sequence with 0 bits, but if you want to know what a sequence with 0 bits looks like, here it is. Nothing. Now, the fact that the bit string is a sequence means that the order of the bits is important. So both of these are bit strings of length 4, but they're not the same bit string. And instead of saying that they're different, maybe a better way of saying it is they're not equivalent. They both have length 4, but, and they both have 3 zeros and a 1, but the ones don't appear in exactly the same place. This one appears as the second bit to the right. This one appears as the third bit to the right. So the ones are not in the same place. The length of a bit and the length of a bit is 1. The length of a string is the number of bits in the string. Now, it turns out that we can do bit operations or logical operations on a string of bits. I'll give an example. Here we define bitwise operations. Given two bit strings of length n. So if they both have length n, they have the same length. So given two bit strings of length n, the bitwise OR, the bitwise AND, or the bitwise XOR of the two strings, is the string of length n that has as its bits the OR, AND, or XOR respectively of the corresponding bits in the two strings. So first of all, if we compute a bitwise OR, a bitwise AND, a bitwise XOR on a pair of bit strings of length n, we get another bit string of length n. So take two bit strings of length n, perform an XOR, an XAND, or a bitwise XOR on the two strings. We get another bit string of length n. And what we do is we compare corresponding bits in the original two strings. And with each pair of corresponding bits, we compute either the XOR, the AND, we compute either the OR, the AND, or the XOR. Now let's look at an example, okay? Compute the bitwise OR of these two strings, 0, 1, 1, 0, 1, 1, and 1, 0, 1, 1, 0, 1. Both strings have length 6. They have the same length. So this operation is possible. Here's the first string. Here's the second string. And we're going to put our answer down here. And we'll call this the bitwise OR. And here's how we do it. We compare corresponding bits, or we apply the OR operator to corresponding bits. We apply the OR operator to the two leftmost bits. We have false or true. That's going to be true. Then we move into the next pair. We have true or false. That's going to be true. Then we go to the next pair. We have true and true. That's going to be true. We have true and false. We have false and true. That's going to be true. We have true and false. That's going to be true. True and true. That's going to be true. Okay. So here is the bitwise OR of those two strings. Now let's do the same thing with the bitwise AND and the bitwise XOR. Okay, here we go again. The same two bit strings of length 6. We're doing the bitwise AND. And again, we compare corresponding bits. The first bit going from left to right, we compare the first bits going left to right, 0 and 1. We have false and true, that's false. Then we compare the second bits going left to right, true and false, that's false. Then we look at the third pair of bits going left to right. We have true and true, that's true. And the fourth pair of bits going left to right, that's true and false, which is false. The fifth pair of bits going left to right, that's true and false, that's false. And the last pair of bits going left to right, we have true and true, that's true. So this is our bitwise AND. And we have one more. We also want to do the exclusive OR the XOR of these two strings. Okay, we're back again. The same pair of strings, but this time we're doing the bitwise XOR, or the exclusive OR. And depending on the special case that we remember, the exclusive OR is only true when the bit values have different values. An exclusive OR is true when we have a true and a false, or a false and a true. An exclusive OR is false when both bits have the same value. Well, let's see. Two different truth values, that's going to be true. Look at the second pair of digits going from left to right. Two different truth values, that's going to be true. Going from left to right, let's look at the third pair of bits. The same truth values, that's going to be false. Going from left to right, the fourth pair of digits, they have different values, so this will be true. Going from left to right, we'll look at the fifth pair of digits. They're different truth values, so they're true. And the last pair of digits going left to right, the truth values are the same, so this will be false. So this is the bitwise XOR of the two strings. You know what? I guess there are a few more things that I need to say. One of them has to do with variations of the conditional statement. So given the conditional statement P implies Q, there are three variations that are closely related to this original conditional and or to each other. So here's the original conditional statement. This is the converse. We just switched P and Q. This is the contrapositive. We switch P and Q and we negate both of them. And this is the inverse. We don't switch P, we don't switch Q, but we negate both of them. Now they are, well, let me be honest. The inverse is really not much more than a curiosity. The converse is important, and the contrapositive are important. Let's find out why. Let's look at the truth tables for the contrapositive, okay? Okay, given the conditional statement P implies Q, or if P then Q, construct the truth table for the contrapositive. And remember how we get the contrapositive? First, we switch these two things around, so we have Q here and P here, and then we negate both of them. So we want to construct a truth table for this statement. And just so that we don't misapply anything, let's put parentheses around the not Q and the not P, so we know that we do what's in the parentheses first, and then we apply the conditional statement operator. So, in the broadest sense, this is a conditional statement involving not Q and not P. So, to get the truth values of this statement, first we have to get the truth values of not Q and the truth values of not P. So let's say not Q when Q is true, not Q is false, and the truth value of P has nothing to do with the negation of Q. When Q is false, not Q is true, and the fact that P is true has nothing to do with the truth value of not Q. When Q is true, not Q is false. When Q is false, not Q is true. There, we have the truth values for not Q. Now we also need the truth values for not P. When P is true, not P is false. When P is false, not P is true. Okay, we have the truth values for not Q and the truth values for not P. We're ready to do the contrapositive. This is a conditional statement. What's the special case for a conditional statement? A conditional statement is false when we have a true implying a false. Does that happen here? Do we have not Q true implying not P false? Let's see. Oh, son of a gun, it happens right here. Not Q true implies not P false. So this is false. And this is the only case where we have not Q true implying not P false. So all of the rest of these things are true. Now there's something that should be slightly familiar about this truth table, but maybe the bells aren't ringing yet. Let's take a look at the truth table. True, true, false, false, true, false, true, false. Let's take a look at the truth table for the original conditional. The original conditional, P implies Q. Now, when is the only time that this conditional can be false? It's when we have true implying false. The only time this conditional statement is false is when we have P true implying Q false. And that happens right here. P true implies Q false, that's false. This is the only time when we have P true and Q false. So all of the other statements are true. Now I wonder why it is that I wanted to do the truth table for the original conditional, P implies Q. I got to get my blue marker out for this. Look at this. True, false, true, true. True, false, true, true. They're the same truth table. So what does that mean? It means that the contrapositive is logically equivalent to the original conditional. Essentially, they are the same statement. So the point of this is that the conditional P implies Q, and it's contrapositive, and like a knucklehead, I didn't write down the contrapositive. Not Q implies not P. The conditional P implies Q and its contrapositive are logically equivalent. So in other words, they're really the same statement. Now, why is this important? Sometimes, especially if the conditional is worded in English, sometimes the conditional may not be that easy for us to understand. But if we write its contrapositive might be a lot easier to understand. So sometimes instead of working with a conditional statement, we'll work with its contrapositive because it's easier to work with. And whatever is true of the conditional is going to be true of the contrapositive, and whatever is true of the contrapositive is going to be true of the conditional. Logically, they are the same exact statement. They just look different. Well, let's see, another thing. This is just terminology, but it might be good if we know this. Given the conditional statement P implies Q, or if P then Q, P is the hypothesis, Q is called the conclusion. So the hypothesis is the thing that does the implying. We get our implication from the hypothesis. Okay, I think this really is the last thing I'm going to tell you. I don't really like to talk about this, but I guess I should. Suppose that we're in a dilemma as to which of these operators we should apply first. Now, if we write a logical statement out symbolically and we do it well, there's not going to be any question because we'll make prudent use of parentheses so that there will never be any doubt what we should do first. But if somebody else writes a symbolic logical statement and it has a bunch of these operators in it, and they don't use parentheses, we might be in a quandary as to which thing we should do first. Here is the order of the hierarchy, the precedence of logical operators. The operators with the highest priority we do first. So if there's a negation operator present, we do it first. Next, if there's an and operator or conjunction, we do that next. Then, if there are any disjunction or operators, we do them next. And I guess there's also a question about, suppose we have a few and operators in the same statement. No parentheses. Which and operator or which disjunction operator has precedence? And the rule of thumb is If we have a bunch of these in the same statement and there are no parentheses, we just work from left to right. So we do the first one of these going from left to right, then we do the second one going left to right, and so forth and so on. Now, if we're writing programs, if we're working with logical statements written symbolically, the good thing to do is to make prudent use of these things, prudent use of parentheses when doing these things. And that way there's never any doubt what should be done first. So I guess I should conclude with an example. Okay, here's a real bucket of worms here. I've got the negation operator, the conjunction, the disjunction. What does this really mean? Well, if I'm a nice guy, I'm not going to write it like this to begin with. But the negation operator has precedence over everything, so we do that first. There. Not P or Q and R. Well, you know what? I'm not done yet because do I do this one first? Or do I do that one first? As far as hierarchy goes, this is done first. Okay? Now the order of operations of all of these operators is completely determined. We do this first, we do that second, and we do that last. It is good to know the order of the operators in case somebody's not a nice guy and they have us interpret something like this. So we need to know the order of precedence. The highest priority is negation. Then it's followed by and, then or, then if then. Let's see. Negation, and, or, conditional, biconditional, from highest to lowest. Just in case we ever have to decipher some piece of junk like this, that we need to know the hierarchy of the logical operators. Not, and, or, conditional, biconditional.